This is TWIS, This Week in Science, episode number 786, recorded on Wednesday, August 12th, 2020. TWIS explains the universe. Hi, everyone. I'm Dr. Kiki, and tonight on This Week in Science, we will fill your head with tiny cleaners, giant alligators, and placebos. But first, thanks to the Burroughs Welcome Fund and our Patreon sponsors for their generous support of TWIS. You can become a part of the Patreon community at patreon.com/thisweekinscience.
Disclaimer, disclaimer, disclaimer. People worry, what are they worrying about today? People worry, what are they worrying about today? People worry, what? Oh, the coronavirus is still experiencing exponential growth in the United States, and politicians, while canceling political rallies, are encouraging children to attend in-person schooling. And there's a safety stimulus thing that's been stalled while there's like 100 million people about to go homeless from eviction, and global warming is still a serious threat. Yeah, but nobody's talking about that right now. Arecibo. Yes, I know what Arecibo is. That's the world's second largest telescope, located in Puerto Rico, currently tracking a very dangerous asteroid that is the size of 5 football fields or 80 tennis courts, if you prefer that. What do you mean it just got ripped in half by a loose tension cord thing? Oh, okay. So maybe there is a good reason to worry. But one thing which you need not worry or fret is that This Week in Science is coming up next.
I've got the kind of mind that can't get enough. I want to learn everything. I want to fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek. I want to know what's happening.
Good science to you, Kiki and Blair.
And a good science to you too, Justin, Blair, and everyone out there. Welcome to another episode of This Week in Science. We are back. That's right, we are back. We said, I'll be back, and now we are back with science, because science never sleeps, and sometimes I don't either, and that's probably not good for me because science says sleep is good. But let's talk about the science, okay? I brought stories about white dwarfs, placebos, and we have a guest tonight to explain the universe to us.
Oh, good. It's about time.
Everyone wave at Daniel Whiteson.
The whole universe will be explained this evening.
Awesome. Okay, Justin, what did you...
Show. We should have done this interview first, and then we probably wouldn't need to done the rest. What do I got? I have the giant, enormous alligators of North America. I have the homelessness story that has no upside.
Blair, what's in the animal corner?
Tiny cleaners that you mentioned. I have tuataras and shrinking fish.
Shrinking fish. They must be related to my white dwarfs.
Perhaps.
We'll see. We will see. All right. As we jump into the show, I would love to remind you that if you are not yet subscribed to This Week in Science, you can find us all places that podcasts are found. We have a YouTube channel and we're on Facebook. Just look for This Week in Science. You can go to our website at TWIS.org. Okay, let's jump into those quick gold stories. Hey, where there is water, there might be life, right? And
Could be.
Could be, maybe.
Everywhere here there is. Everywhere here there absolutely is.
Yeah. Well, a series of papers in Nature this week support the idea that a salty ocean, probably muddy and salty, exists beneath the icy surface of Ceres. The ball of ice that floats just past Mars in the asteroid belt was imaged by the Dawn mission, which showed variations in this Texas diameter planetesimal's gravitational field that are indicative of pockets of salt water. which is very cool because it was thought that once upon a time there was an ocean underneath the frosty ice surface, but they were like, oh, well, it's probably frozen up and it's not there anymore. But evidence says that it is. So additionally, they have some high resolution images that also tell a story of these ancient impacts that occurred that cracked that icy shell and allowed some of that salt water to seep up to the surface where it's visible today. And Dawn actually first imaged these spots as white spots. They were reflective white spots on the surface of Ceres. We were like, what are those things? Could it be water? And indeed, they really think it is. Back in 2015 was when it was first imaged. The finding implies, because it's water, salt water, that the conditions for life could be closer to Earth than previously thought. So instead of having to send missions way out to Jupiter or Saturn, we could be going to the asteroid belt.
That image of Ceres was one of my favorite astronomical images because the first one they got that showed the bright spot also made it look like it was a pyramid. Like not just something that looked a little bit like a pyramid, but like a serious like Egyptian pyramid. And so for a while, it felt like we were in the beginning of a science fiction novel, where they're like, why is there an obelisk? It was pretty exciting. But, then they took pictures from the other side and it didn't look nearly as much as a pyramid, like a pyramid.
Oh,
did.
They should have never
triangulation and multiple points of data collection. Oh.
They never should have reimaged the face on Mars. They should have just been like, yeah, that's there. Deal with it.
Yeah, some of these high resolution images, one of them, they've been able to determine that there's a mountain near one of the white spots that's like 21,000 feet tall, I think. My units of measurement are not accurate in my memory.
There's a really
at the
big
moment.
mountain.
Exactly.
But it's
a lot
taller
of units
than
are big.
It's bigger than Denali. It's very tall, very high on a little tiny Texas diameter dwarf planet, which is pretty cool.
It's amazing. I think a lot of people don't realize how much water there is out there. Like we think of water as an Earth thing, but really there's like huge amounts of water out there in the solar system. Of course, most of it is ice, right? But there's a lot of water out there. So there really are a lot of places where life could still exist in our solar system. That's incredible, right?
Our water may have come from somewhere else.
Oh, absolutely. Very likely did because early Earth probably boiled off most of its water. So we're swimming in, oceans of melted comets, most likely.
Yes. I like thinking of that. I'm going to go comet ocean swimming. Yes. I will remember that next time I go swimming. Yes. All right, Justin, tell me about these ancient alligators of North America.
Okay, this is a new study. It's revisiting some fossil specimens that were previously collected and some new finds of this enormous crocodilian. It's a Deinosuchus, which is, they're calling it a crocodilian, although they're also going to say in the study that it much more resembles a modern day alligator in terms of lineage, but still, whatever it is. They found that this thing's teeth, finally. They found a sample of these teeth, which they are describing as banana-sized teeth. Which
Those are some big jumpers, yeah.
Those are some really big teeth. And then you can start to get a feel of how, because you can picture a crocodile in your head. The teeth are not that big. So this is, scaling up. You have, right. So it's 33 feet in length, this thing. They review this is published in the Journal of Vertebrae and Paleontology. It also reveals that there were different kinds of them for different species that lived in North America. There were 2 species that lived in West America that ranged from Montana to northern Mexico. There was another that lived Atlantic coastal plain from New Jersey to Mississippi, which at the time they're saying this North America had, and this time frame, where's my time frame? 75 to 82 million years ago. There was a shallow sea that connected the Arctic Ocean with the Gulf of Mexico. So there was, which I did, that's a fun fact. I had no idea that was there. But it explains the predominance of these giant alligators. They'd previously found remains of other dinosaurs, or of dinosaurs that had these bite marks on them that they hadn't been able to really connect to anything. And now they're sure, yes, this thing was eating everything. It could eat the biggest predatory dinosaur in its environment 80 million years ago. Not a problem. This thing was an apex predator. And it lived in water and would hang out there. So, dinosaurs, they needed to drink probably takes a while for a dinosaur to get a decent drink of water, right? For that size.
It needs a lot of melted comet.
It needs a lot of melted comet to keep the dinosaurs fueled up. So they had to go near the water, and then these things would be waiting. One of the interesting things that I kind of found about this that they discovered in this that I found interesting was they found these two holes at the front that they haven't really, it's a feature that they don't see on modern alligators or crocodiles today. It had this enlarged nose area and these two holes that they can't, I'm sort of picturing them though, if I'm going to guess and speculate here, that they have like nostril snorkels. Because you can sort of see it already, like the way a crocodile or an alligator will sort of hover under the water with just eyes, maybe a little bit of nose up there. So if you could have a snorkel that went up, even better. And then you could really hide, because you don't want a predatory dinosaur to see you first. There's a chance a T-Rex or something could make the meal out of you. You really got to sneak up while being 33 feet long. It was a tough balance.
So modern day saltwater crocodiles, the largest of the current crocodilians, they can get to be about 20 feet long. So not nearly this big, but still pretty darn big. And they also they have the kind of the bulb at the front where their nostrils are. So their ears, their eyes, and their nose are all just above water. And they can stay in very shallow water, these giant 20 feet crocodilians. And so they blend in really well in the muddy water, and a gazelle comes up to drink or whatever, and bam. So it's a pretty similar strategy, just I guess extra large.
Especially with those banana-sized teeth. Got you, gazelle.
Yeah, that's really something. Like you go, okay, banana-sized teeth. Then like picture holding a banana.
Yeah, that's one tooth.
That's a singular tooth.
You have to have a very large head.
Prehistoric bananas.
Yeah, right.
They ate everything. They ate absolutely everything.
They ate whatever they wanted.
Yeah, they did.
So what happened to them? Why aren't they around anymore?
So that's a great question. So they don't know. So they apparently so far they think they have disappeared before the meteor impact. Before the event that knocked out the dinosaurs, right? So they don't have that as its endpoint. It seems to end sometime before this. So who knows? Well, maybe we're talking a climate thing where the inland sea dries up. I don't know. They don't know.
There has been speculation that there was climate change going on before the asteroid hit. And so the asteroid just exacerbated what was already a slow decline. So, who knows?
The snapshot that we have in our heads of the current crocodiles being unchanged throughout time, this is a very radically different part of that lineage that shows we got to keep thinking of everything being as evolved as us. Everything has had this much time to go through evolution and to make adjustments. Although, it looks like at least its hunting practice may not have changed in all of this time.
Yeah, the sit and wait predator is an efficient method for sure. Yeah.
Well, I've been sitting and waiting here to hear about these tiny cleaners.
Oh, yes.
You brought.
Oh, yes. So a lot of people don't realize that coral are animals, but hopefully listeners to the show would be familiar by now that I've hammered it into everyone's brain enough times. So corals are animals. They're actually little polyps. They look almost like teeny tiny anemones. And so they're filter feeders. They can grab onto little particulates in the water like that. They come out of the little coral shell and grab little bits, and they can suck back in when something swims by, or they want to protect themselves, or any number of things. So that's how a coral polyp works. And so this is a study from the University of Warwick, led by Eindhoven University of Technology in the Netherlands. They wanted to turn this technology that we see in corals, use some biomimicry, and turn that into something that we could use. So they actually developed a 1 centimeter by 1 centimeter wireless artificial aquatic polyp that can remove contaminants from water. They have a rotating magnetic field under the device that drives a rotating motion of the artificial polyp stem that then results in a generation of attractive flow, which guides targets like oil droplets towards the polyp. And then a UV light is used to activate the polyp's tentacles, which has photoactive liquid crystal polymers that bend towards the light, enclosing the passing target in the polyp's grasp. And then you can also release the target with blue light. So they think that they'll be able to clean out water, but even more interestingly, potentially, is that they also think they could use this technology in medical diagnostic devices by being able to pick up and transport specific cells.
Wait. Specific cells? Like, that's
they're
amazing.
that tiny. They're that specific.
I wonder if they would use, in order to catch specific cells, if they would use chemical attractants or, like immunological markers or antigens to be able to do that kind of capture. I wonder how they would go about managing to pick out certain cells over others.
Yeah.
They probably have machine learning in there like everything else these days, right?
Yeah, absolutely. You could learn from its experience.
Somebody needs to stir it with a hand crank to keep the fluids rotating around long enough for it to come into contact. That's probably, a combination of technologies involved.
High tech and low tech.
Sure. Yeah, so little coral polyps cleaning the ocean, potentially saving your life.
Brilliant.
That's amazing because corals are going extinct, so we have to make synthetic ones.
Oh, no.
The oceans are going to die, and so are all the corals.
Our synthetic trees that we're going to make that are going to be solar panels and also convert carbon dioxide into oxygen.
We're just going to
do photosynthesis instead. Let's just create a fake world. Just start it all over.
Biomimicry for the future. We will win.
Or we could change our ways, but
we could. So I was going to talk about the damaged Arecibo dish, but Justin brought that up in the.
Oh, I just mentioned it. I don't bring anything more about it. Yeah.
So just really, you got the big details. In the middle of the night on August 10th, a steel support cable snapped and it was pulled taut, so it went spring and then flopped around because there was a bunch of tension in the wire. And because it's a steel cable supporting this massive 307-meter dish, it ended up destroying a 30-meter section of the Arecibo radio telescope. And so the pictures of it are awful. There's just bits and pieces of the dish on the ground. And an additional antenna called the Gregorian Dome was also damaged. And the telescope is totally offline until repairs can be made. And they don't know whether that's going to be days or weeks.
What if the aliens are calling us right now?
Out of luck.
Well, if the aliens are calling us right now, we do have other telescopes that are radio astronomy telescopes that are looking out in the way that Arecibo does. And actually, as Arecibo has been kind of fighting for its survival for several years because there are larger telescopes now. There are more accurate, more powerful telescopes.
There's one larger.
Yes. And there are others in planning. And
more
so
sophisticated.
More sophisticated. Yeah. It's the funding. NIH has, not NIH, NSF has pulled back funding. They are not funding it as much. The University of Florida started funding it more. But now with this damage, we'll see. Hopefully it will continue to do wonderful work because Arecibo, it's amazing. Well, speaking of more space stuff, 12 billion years ago, there was a galaxy like the Milky Way. 12 billion years ago. A spiral galaxy, ordered, not chaotic, very nice looking. Something you'd bring home to meet your parents. It's super weird because we've never found anything quite as ordered that far back in time before. So this is, a couple of billion years after the start of the universe.
Which sounds like a long time until you got to form a whole neat little social, galaxy like that. Is this going to push back the age of everything?
I don't think it'll push back the age of everything, but I think it just, in terms of galaxy formation, it does pose some interesting questions as to what forces, and Daniel, you can maybe correct me here if I'm thinking incorrectly, but what forces would be necessary to lead to an ordered structure as opposed to a more chaotic structure in the early, more energetic phase of the universe. I mean, this is a period of time when the galaxy had a large amount, the area of space the galaxy is in, there's a large amount of star formation, it's super active, and normally when that's going on, it's going to be dusty and gassy and pushy, not all neatly spiraled up like Princess Leia's hair buns.
Yeah, and these spiral galaxies often form from mergers. Like you get a couple little proto galaxies that come together and they have angular momentum. You get those spirals. So it just takes time. I mean, like, how long would it take you to make a spiral galaxy, right? You'd
A
still
very
be doing
long
it
time.
in a billion years or so.
Yeah.
So you're right. It's fascinating to look that far back and be like, wow, there already were galaxies, because they run the simulations and they can't really explain how you get that stuff so early. Like not just the galaxies, but also the supermassive black holes in the centers of galaxies. Some of them are already like 1 billion times the mass of the sun when the universe is like 1 billion years old. And they don't know how to make them that big that fast. So it's fascinating.
Yeah, the biggest ones I was looking at some infographic that was showing like a 6.5 billion or more, like just when you start to contemplate, those are talking about solar masses. And those billions of that's a big collection.
Because even really one solar mass is ridiculously big, right? It's like,
well, to us, okay, to us,
yeah, exactly.
But to a big black hole, that's nothing. Don't even notice it.
Yeah. That's
it's
breakfast.
Yeah, exactly.
So what do we base this the age of our universe on, if not the oldest structured things that we can see?
Yeah, well, that's a great question. We do it a few ways. One is, what is the oldest thing out there? But these aren't the oldest things. The oldest things out there are things like the cosmic microwave background radiation, which is even older. It's like 400,000 years from the beginning of the universe. But then we just look at the expansion. We're like, the universe is expanding. Let's just run the clock backwards, and see when t equals 0 is. So there's a few ways that we measure the age of the universe. And the cool thing is they mostly agree, to within a couple 100 million years, give or take. So that's pretty awesome.
That sounds pretty good. Yeah.
Yeah.
That's very awesome. I keep wondering, if there were ordered galaxies that far back, what does this mean for intelligent life in the universe? Dun, dun, dun.
Yeah.
Just put that thought out there. I have one more quick story for those of us who do want to live as long as we can. Yeah, Blair is very excited at this
here
one.
for it.
Yes, you are. So could we slow down aging if we knew what the indicators of accelerated aging are? Scientists have been trying to address this question by studying dolphins. Of course they were. Well, actually, dolphins have lifespans that are long, like humans, and so they make a great comparable species to look at. And so they did a longitudinal 25-year study, and they looked at 144 dolphins that were housed by the U.S. Navy, because yes, we all know this, the U.S. Navy loves dolphins. They measured a bunch of stuff in the blood and found 4 markers that can be used to measure aging differences in dolphins, not in people, just dolphins. Hemoglobin, lymphocytes, platelets, and alkaline phosphatase. Alkaline phosphatase is indicator of liver function. Platelets are a blood factor, lymphocytes, immune factor. Hemoglobin, that's your red blood cells. And as people age faster, often they become hemoglobin deficient, and it leads to age-related anemia. So these levels indicated faster or slowing aging dolphins. And if these same markers can apply to humans and are aging, then maybe doctors and others can look at stuff like hemoglobin to inform the development of treatments for things like age-related anemia. So potentially, these factors could go on to help us live longer lives.
If we're dolphins.
If we're dolphins, yes. Which
I definitely want to retire to the U.S. Navy's dolphin nursing home. That sounds like a great place to hang out.
If you just tuned in, you are listening to This Week in Science. And if you're interested in a TWIS shirt or a mug or other item of our merchandise, you can head over to twis.org and click on the Zazzle link. We have face masks also. TWIS masks. Show the world you care about them and that you love TWIS. All right, I would love to now finally really officially introduce our guest for the show. Dr. Daniel Whiteson is a professor of physics and astronomy at UC Irvine, where he investigates questions related to the fundamental nature of our universe using experimental high-energy physics. Things smashing together. Whiteson is a part of the ATLAS collaboration at the Large Hadron Collider, created an app to turn cell phones into cosmic ray detectors, and has published several comics and books attempting to explain the universe. You might know him as Daniel from the podcast called Daniel and Jorge Explain the Universe. Welcome to the show.
Thanks very much for having me on.
You're welcome. Thank you for joining us tonight. It's just wonderful to have an expert in the universe join our show.
I have an all-encompassing expertise. That's right. No, we like to talk on our podcast about basically everything inside the universe, and so that's why we went with that very broad name.
I think that makes sense. But how did you initially become interested in the universe?
In the universe, well, I live in the universe, and I figured I'd like to understand it. And I have some questions, and I never really got answers to those questions. You know, I grew up in Los Alamos, New Mexico, the home of the National Lab of the Manhattan Project. So physics was sort of always in the air, but I always had basic physics questions, you take a rock, you smash it against another rock, you get smaller rocks. You keep doing that. Do you just keep getting smaller rocks, or eventually do you get to like the smallest possible rock, or does it turn into something else? So these are the questions I would ask as a kid. And so I never really got answers to those questions. I'm still trying to figure them out. Science is like just a group of people trying to answer their own personal weird questions about the universe or nature or whatever. And this is my personal weird question: is I want to understand things from the very, very smallest bits.
Do you believe it's turtles all the way down?
I would love if it was turtles, man. I want it to be something totally weird and mind-blowing. Yeah. But I would hate if like some theorist came out there with some idea for how the universe worked, and then we found out, yeah, that's true. I want to discover something strange. I want to be like, actually, it is turtles. Oh my God, look at these little weird turtles waving up at us from the, the Planck scale or something. So that was a joke. But no, I think that there probably is a smallest thing. I think that there is an answer to this question. It doesn't just go on forever to smaller and smaller and smaller bits. I think there probably is a nugget, a basic building block of the universe that reveals like something deep about how the whole universe is put together. I want like that level of answer, like the constructor of the simulation, what pieces did he or she use?
I'm going to steal that as a now forever interview question. What is your own personal weird question that you're trying to answer in your field? That's fantastic. I like that take. I'm stealing it, but I'm going to use it in good faith. Do you think there's a something?
I think there's a something because, we take the stuff that's around us. I and you, we're all made out of atoms and molecules. You break those open, inside of those, you got protons and neutrons. You break those up, you got quarks and electrons. That's sort of like our current state of understanding, the most basic building blocks. But we know that it's not it. We know that's not the final answer. First, because they're like weird patterns among all these building blocks that have no explanation, that like are really strong hints that they're probably just made out of smaller bits. Like you look at the periodic table and there are patterns in it, right? And before you knew that the periodic table was made of smaller pieces, you'd wonder like, how come these guys are all metallic and these guys are, are inactive and whatever? You wonder, what are all these patterns? And of course, now those patterns are just huge clues that tell you, oh, it comes from the structure of the atom, how they're put together. Well, we have the periodic table of the fundamental particles, 6 quarks, 6 leptons, and we see patterns in them, similar kinds of patterns, not the same ones, but in spirit the same. And we wonder, like, why are there, for example, 3 kinds of quarks? Yeah. Why do the quarks and the leptons balance each other electrically when there's no relationship between them? I could go on and on about all the weird things we see in these particles that tell us there must be something underneath that explains it all, something akin to how the atom is put together, a simpler puzzle piece.
So there's something that this also puzzles me, and it's within all of this, there's always a point where I get to and trying to understand it, and then there's a feeling that things are not consistent with time. There's not a persistence of things in a place going and traveling like we would picture a thing moving in space. There's inconsistencies where things are when it comes to our experiential perspective of time. How does time play into trying to find a thing?
It's a great question because we try to understand the microscopic world and we try to do it in terms of the things we know, right? So I say particle, you probably think tiny little spinning ball, right? Because you can only think about it in terms of things you know. It's like you eat a new fruit for the first time. You're like, it's a little key mixed with a grapefruit or whatever, right? So when you encounter a quantum object, the electron, you're like, well, what is it most like? Problem is, it's not like anything, right? It's like a little bit like a particle. It's a little bit like a wave. It's mostly like nothing we've ever seen before. And one of the ways it's weird, as you say, is with time. Like, for example, particles at the quantum level, they don't go. They don't move, right? It's not like they have a path where like you were here and you were going in this direction, so now you're here. You know, if you throw a ball, you say, well, the ball started here and it ended here. Therefore, it was at every place in between, right?
Right.
Particles don't do that. They don't go. They don't smoothly move from one place to the other. They have snapshots. They're like, I'm here. I'm there. That doesn't mean I was in between. You could have like an impenetrable barrier in between. No big deal. I don't have to be in between my locations. So like, yeah, it's mind bending.
Blair, you look very upset at this whole concept.
It's a lot. I mean, learning these kind of concepts in school, you kind of accept there's something that the teacher's not telling you. Like, okay, they're dumbing it down for me, but they know really what's going on.
But they don't.
Actually, they don't.
Well, that's my favorite part is that, random people who ask questions about this have the same questions that we do, right? Like all these questions, what is the smallest piece? How did the universe begin? Those are the same questions that animate scientists today. Like we would love to know the answer to those questions. And that's why I like to tell people that, everybody's individual weird questions is what pushes human knowledge forward, because people are just like, no, I must understand. We'll keep digging in the knowledge mines until I figure this thing out, and so far, we don't know.
I kind of like that analogy of like the magician being asked to reveal how they do the trick and just going, no, I really don't know. I'm amazed with everyone else here that worked every time. But
it wasn't in my hand, and then it was in my hand.
Honestly, the first time I did it, I freaked out too. But now, I use it at parties as a trick.
And it's both like frustrating because you'd like to understand it intuitively, but it's also awesome because it's sort of the whole idea. Like we want to pull back a layer of reality and figure out how things really work. It'd be kind of boring if things were just like smaller and smaller, tiny physical balls all the way down. It's much more fascinating to pull back a layer of reality and be like, what? We thought it worked like this way. That's totally wrong. It's completely different. You have to revolutionize your whole relationship with like the universe. Those are the moments in science I'm around for, right? When you figure something, when you see something, you're like, this blows up everything. Like that's what I want. That's my personal scientific fantasy, is to discover that actually are tiny little turtles or boomerangs or strings or whatever, and make people go, huh? How can that be?
How did that happen?
Yeah.
So you, with the experimental high energy physics, you take these tiny, not balls of things, and shoot them at each other and see what happens. Working at the Large Hadron Collider with the ATLAS experiment. I mean, this is where the Higgs boson was confirmed, which was a major pillar of the standard model of physics theorized forever. But then
50 years.
Experimental physics finally gave the evidence that it's that our standard model's right, that boson was there. What has been happening recently at the ATLAS? What is like, have we gotten anything that's kind of tantalizing as to, the tantalizing weird turtle, or is everything still kind of like, This is we're fine. We are confirming everything. What's going on?
Well, we have not seen anything weird yet, right? We have seen everything we expected to see, including the Higgs boson, which is pretty cool. But we haven't seen anything new. And, you have to remember that this is exploration. Sometimes you get a good hint for like what you might see when you go land on that alien planet. Sometimes you don't. And so we thought the Higgs boson would be there. We found it. That's cool. And then we had various ideas for what else we might see when we collided these particles. Because remember, colliding particles gives you like a window into the basic universe. What happens when you smash the proton and the other proton together is you make this little ball of energy. And then nature gets to decide what to make out of that. It's not like chemistry where you rearrange the bits of the proton into something new, but you're stuck using the original bits. It's alchemy. It turns into energy, and then you can make anything. You don't even have to know that it's possible. You just have enough energy and you can make it. So it's really like anything on nature's menu. And that's why we try to crank as much energy as possible. So every time you get like a new piece of energy, a new level of energy where nobody's looked before, it's really akin to like landing on an alien planet for the first time and exploring. You don't know if you're going to be met with a parade or there's going to be pink elephants or it's just like dust and rubble, right? But that's why we explore, because we hope to find something weird and new. So that's a long way to say we ain't found nothing yet. But it's exploration. So we never know what's around the corner. And, we didn't know when we build it if there were exciting discoveries waiting for us or nothing.
Yeah. And so the power that the collider and the Atlas experiment are working at now, is the experiment not just with COVID, but is it shut down currently for improvements?
Upgrades,
strength
we call them.
upgrades. Yes.
Yeah, we run for about 18 months and then, things break down and we have ideas for how to improve them. And then we turn it off and we warm everything up, which takes a few months. And then we go down there and we replace stuff and we upgrade stuff, we improve it. And then usually also they tweak the collider itself to make it a little higher energy or higher rate, like more collisions per second. Because if you're looking for something really rare, like something that happens once every trillion or quadrillion collisions, then you want as many trillion and quadrillion collisions as you can get. And so right now we're in the middle of a shutdown, and we were supposed to finish that shutdown late this year. But of course, that's been delayed due to COVID because people can't go in and work on stuff until sometime next year. But, there's still a lot of stuff we're hoping to see, and a lot of the stuff that we haven't even really looked at yet. Like we get so much data. Petabytes and petabytes of data when this thing is running. It takes years to comb through it. There could be a crazy particle discovery like sitting in the data right now on this laptop that blows our minds and revolutionizes physics. We just haven't yet gotten around to looking at everything.
Yeah, I saw something recently about a subatomic particle that had something like a 3 sigma significance that's coming out of the Large Hadron Collider, and it's like, okay, well, it's so funny. I look press releases and I'm like, only 3 sigma. That's not worth reporting on.
No, you shouldn't.
I'm not talking about it until it hits 5.
Yeah. And there's a reason for that, right? 3 sigma means it's unlikely to be a random fluctuation. But, how unlikely? It's like 1 in 10,000 or so. And we do a lot of looking all the time. So if you, flip a coin, if you roll a die 10,000 times, or you get 10,000 monkeys in a room, like you're pretty likely to get something close to Hamlet every day. And so we got to see something really weird and really big because we're looking in so many places all the time. And even still, we haven't looked everywhere. There's a bit of like, I don't know, theoretical blinders on the community, in my opinion. Like the theorists have ideas for what we should see. And most experimentalists are going to look for those ideas and leaving lots of the territory just unexplored. And so I think that a lot of the stuff that we could discover, just nobody's looking for it because it's not cool right now. And,
So if the theorists aren't publishing the papers on it, that's not where the experimentalists are going. There's no papers. So why should I dig in this other area? I'm not a theorist.
Yeah, well, I think experimentalists should be explorers. I think we don't need to know that it's going to be there to find it. We just need to go sail out into the ocean and run into some crazy new continent, right? Or land on a weird planet. We don't need to know it was there to find it. But we've gotten into like big science and you devote a lot of resources and so it has to be approved and whatever. I even had the experience where I wanted to look for something in our data, and they said no, because there's no theory paper about it. So then I went and found some theorists and wrote a paper with some theorists about it. All right, now can I look in our data? And they said, yeah, now you can look in the data. So, and then it wasn't there, but
But at least you got to look.
Yeah,
exactly.
When people talk about space exploration, it's not that I don't like space exploration. I think it's fascinating, but I also sometimes I'm compelled to say, but what about exploring our own planet? Because there's parts of the ocean we don't know very well. Now I'm going to have two. I'm going to want to say we need to explore our own planet. We also need to explore our own matter more closely.
Yeah. Yeah, but it shouldn't be an or, right?
Right, of course.
Each of these things, we want all of them. They're not zero-sum games,
Yeah.
And it goes back to what you were saying earlier about these things are not expensive. We have all these opportunities in science where we could literally just buy knowledge. You give scientists $100 million, they tell you the answer to this important question. Wow, why are we not doing that all the time?
Give the scientists the money.
Yes, just give them the money and learn amazing things about the universe. It should be bipartisan. Everybody should be in favor of learning awesome things about the universe, great technological spin-offs, awesome economical feedback, economics revitalization. I don't get why it's not more popular.
Right. So from Blair's analogy and what you've just brought up, the space program has brought us all sorts of technologies that have made it to consumer level, where it has impacted society from the levels of research and government and policy all the way down to, spam and Velcro on your shoes, right? So these advancements are affecting us, and that I'm sure from the technological advancements that are necessary for high energy physics. The Large Hadron Collider is one of the most advanced, if not the most advanced device on the face of the Earth. And there's also what is it? LIGO and Virgo, the gravitational wave detectors. But to be able to do these things, technologies have to be created. Advancements needed to be made, and those will end up making an impact.
Yeah, and you never know. Is it going to be next year, in 10 years, in 50 years? You never know. But basic research has always paid off. In the long term, it's always a good investment.
It also sounds like the data you've been collecting too. It's not we did all these experiments and we didn't find anything interesting, so we're going to move on. That data is still there to be mined for the next 20, 30, 40, 50 years. And I love the description of it's just because nobody's written a paper on it. People can now write papers and go test it against some already done observations, which has not been something that's been possible before. How long was it where the Higgs boson was found on paper until it was actually observed in nature? We were talking 50 years, 70 years, something like this.
Yeah,
50 years. So now we have the observations outpacing perhaps some of the theoretical, which is that's kind of a fun thing because now there's already a way to sort of test your hypotheses, test your findings on.
And you want it to be is that if somebody has a great idea in 5 years, you can go back and say, oh, well, maybe we have evidence for that in our data that we took. So absolutely, we're not just checking the data and then throwing it away. We're keeping it, and we come back and we look at it all the time because people have new ideas. Just last month, we had a new idea for how to look for dark matter in the collider. Maybe we could be producing dark matter in these collisions and study it in this cool way. And so we're always coming up with new ideas for how to use these collisions because they're very general, how to use them to answer really interesting questions about the universe.
Have you created an app to create dark matter or search for dark matter yet?
I haven't figured that one out yet. No, nobody knows how to see dark matter. It's frustrating because, and dark matter is all around us. We're swimming in dark matter.
Right. Fact, Kiki wants a Snapchat filter for the dark matter.
I do.
Oh, man.
Dark matter over there.
That would be Nobel Prize right there. Right? If you could see the dark matter, it's one of the biggest open questions in modern science. If you ask me, is what is this stuff? We know it's all around us. In fact, we're probably moving through a wind of it because the Earth moves around the sun, right? And so probably there's a dark matter wind in your face right now that you just can't feel. or here.
Or here. No. But tell us about I love the idea that you came up with for the cosmic ray detection with cell phones. How does that work? Why does it work?
Yeah, that's a fun project. Well, the Earth is being hit by cosmic rays all the time. Cosmic rays are just particles from space. So like a proton, super high energy, hits the Earth's atmosphere. Think of it like a tiny little asteroid, right? Big one killed the dinosaurs, tiny little proton-sized meteor from space. And the cool thing about them is that we don't really know where they're coming from. And they have like ridiculously high energy, like much higher energy than anything we make here on Earth. And higher energy than anything anybody thinks can make these anywhere in the universe. Like you ask an astrophysicist, what's the highest energy particle in the universe? They're like, all right, take a supernova, slingshot it around a black hole, do everything you can. They get to like within maybe 1,000 of these, a factor of 1,000 of these particles. So we see particles hitting the Earth and we don't understand what or who can be making these particles. And so it's a fascinating mystery. And one way to study them is to look at these big showers they make in the air. Particle hits the atmosphere, it knocks into other particles, leaves these big showers. And the problem is that we just haven't seen enough of them. So we have really big detectors, one in Utah and one in South America, that are like 3,000 square meters to try to capture one of these showers. But they're rare enough that you just haven't seen enough of them. And so I thought, well, wouldn't it be cool to be able to like build an Earth-sized telescope to capture all of the ones that hit the Earth? And that would cost $1 gazillion. So we thought, well, can we do it using already existing technology? And so there is a piece in your phone, which is just the camera. And the camera is basically just a little particle detector, right? Like there's a piece over it where the photon gets turned into electrons, and then it uses a little piece of silicon and it strips those electrons out of the silicon. And that's a particle detector. We use the same technology at the Large Hadron Collider to look for particles. So we wrote an app which when your phone, at night, when your phone is like camera down, it turns on the camera. And if it sees a little blip in the video, it says, oh, that was probably a particle. And if a bunch of phones nearby all see blips at the same time, that was probably a big shower of these particles. And if you get enough of them, you can like point back and say, oh, this is a big shower that came from over there in space. And so we had this fun idea one time, like over coffee, and we're like, hey, that'd be silly. Oh, wait, maybe that's not so silly. I wonder if we could actually do that. And so then we wrote the app and we got it running and we did some calculations to see like how many phones would you need to like actually do science with this. And it turns out you need something on the order of like 5 to 10 million people to run the app in order to like build a worldwide telescope that can do science at the level of like these $100 million facilities. So I thought, well, that's a lot of phones, but it's a tiny fraction of the phones out there, right? There's like billions of phones. There's 5 million phones turned on every single day. So
for sure,
like sneak it into the next, Google release or whatever, and we'd be set. So that was the idea. We wrote the app, and now we are working to make it like more robust, not drain your battery, be high performance. We've put some phones into particle beams to test their performance. So we're gearing up to have a big wide release when it's like really ready.
What kind of is it just the same? It's not. Is it not enough of a blip to register as a photon that the camera would recognize? Like, what is the difference in the signal from the cosmic ray blip from the normal photon that it detects?
It doesn't look any different, right? And like every time you take a picture, there are cosmic rays in that photograph. They're just like noise in your pictures. So if you put like black tape over the camera, then the photons can't penetrate anymore. And then all
cosmic rays can.
Cosmic rays still can, exactly. Muons and high energy electrons and all sorts of crazy stuff. Yeah, exactly. And we've seen some of these. Like we if you go higher up in the atmosphere, there's more radiation from space because there's less of a buffer protecting you. And so if you're on a plane and you run the app, you see all these streaks from particles. Yeah, I know. Air travel is dangerous for other reasons, right? Not just COVID.
I think cosmic rays, regardless, is just not high on my list for concerns. Just nope.
Yeah, so that's been a fun project, but that's just sort of like a side thing. Like, let's see if we can do this crazy piece of science for basically no money as a fun side project.
Yeah, what's the name of the app? So
it's called Crayfis, Cosmic Rays Found in Smartphones. So Crayfis, and you can find our website crayfis.io or just Google for it. And we wrote a paper, and we're not members of the cosmic ray physics community, and so we wrote this paper and put it out there, and they were just kind of like, "What are you people doing?" It was
You're like, "Why not?"
Yeah, exactly. Hey, I don't know.
Let's
half
try
the community was like, "That's a cool idea." The other half were like, "You're crazy. That'll never work." So it was a lot of fun, sort of sociologically, to enter into a adjacent subfield of science where you're not established.
And you do so much, though. I mean, you've got your research focused. You've got this kind of a project where you're kind of coming up with neat technologies and neat ways to look at different questions. But then you've also got science communication. You've been working with Jorge Cham for years now, doing comics and a couple of books. Two books now, and you'll also have a PBS program coming out, and you have your podcast.
Yeah.
How did you get so involved in communicating science? And like, did you trip over Jorge one day? What happened?
No, I just always wanted to share the stuff. I think it's really fun. I think this kind of wonder belongs to everybody, like, what is everything made out of and how did it start? And everybody wants to know the answer to that question. Like, I sit on an airplane and somebody's like, "Hey, what do you do?" I say, "Oh, I'm a physicist." They're like, "Bleh, I hated physics in high school," like standard. And then I say, "All right, I'm just trying to figure out how the universe started." And they're like, "Oh, really? How did the universe start?" And then you connect to their questions because everybody wants to know these questions. So I thought it was like back in 2008, I was an assistant professor, and I was thinking, what's a better way to communicate this stuff than just like talking about it? And so I thought using comics and cartoons might be like accessible, because comics are, they take down your defenses. They tell you like, "Hey, I'm not fancy. This isn't serious. We're just talking about fun stuff." But I don't have any artistic skill myself. And I was a huge fan of Jorge, of course. Everybody in academia knows Jorge is like a celebrity. He's, he's a group therapy us all through grad school. And so my wife, who's also an academic, she's like, "Oh, why don't you just email Jorge Cham and ask him to do it?" And I was like, "You can't just email a celebrity and ask them to do a project with you. Like, what am I going to email Brad Pitt and be like, 'Hey, be in my movie'?"
Actually, it works. That's how. Yeah, that's how that works.
It is how it works.
He's been sitting around. People are so afraid of approaching him. He hasn't worked in a long time. He's just like, "I'll do anything," but nobody's emailed or called me. I'll just stay home and watch Netflix.
Yeah. So I emailed him, just cold emailed him and said, "Hey, I have this fun project. Would you like to collaborate?" And he was like, "Hey, that sounds cool." And so then we got started, and then we just had fun. And so we did a bunch of videos, and a few of them went viral. Like, we put out a video about the Higgs boson just before it was discovered, and it went all over the internet, and that was really fun. And then we wrote a book called "We Have No Idea," all about like the big unanswered questions of the universe. And that was a lot of fun. And for me, like, I'm mostly trying to be a research scientist and teach. I'm doing that whole professor thing. And all of these things are like fun side adventures. Like, sure, I never wrote a book before. What's that like? Let's try it. I don't know. For me, like, if any of these things, if I embarrass myself or fall flat on my face, like, I can just go back to being a physicist. So it's like, sort of like low risk. And I have like huge respect for people who like leave their day job and dive into and do these things full time, because that's, you're really taking a chance on yourself. I was never that brave. And and so we've just been having a lot of fun working together ever since. And a couple of years ago, PBS reached out to Jorge and said, "Hey, have you ever thought about doing a science show for kids?" And he called me up. He said, "What do you think? Should we try to do a science show?" And I said, "I don't know. Let's try it." So we put together a pitch for a show, and it's all about a bunch of little curious animals that wonder about the world and then figure out the answers themselves. They don't like go ask parents. They're like, how do we think about this? Or how could we figure this out? And they use very simple, basic science practices. It's for like 5-year-olds to get them to think like, have a scientific mindset and to encourage their curiosity. And we sent it in, and, like with grant proposals, you send it in, you expect to never hear back. But then they called us up. They're like, okay, make this show. And we were like, what? I'm Googling like how to make TV show. Like, I wish that was a joke, but
how do I do this? Yeah.
We figured it out, and it's coming out on PBS next month. It's called Eleanor Wonders Why, and it's on PBS Kids, and it's all about wonder and curiosity and the joy of discovery and figuring stuff out. And it's been a crazy experience, but a lot of fun.
I think that's such a skill that I hope that we can teach to younger generations, the figuring stuff out, that curiosity. And, it's not always in a book, like we were talking about at the beginning. The teacher, the magician doesn't always know the answer. And, but there's still that process of figuring things out. And all of us can do that. I hope you have at least one episode of these little animals figuring out that the earth is round and going through that process of confirmation.
Debunking conspiracy theories.
There we go.
The curriculum for the show is actually more life sciences, which is funny.
Okay.
It's not physics, but it's for 5-year-olds. So it's basic stuff. It's like, is a rock alive or not? Why do birds have feathers? And the research I did is like, I walked around my neighborhood, which has lots of kids, and I was like, hey kids, what questions do you have? And, they told me about stuff like that. They're like, did you know cats can have babies? Oh my God. And, these little moments were like, your mind is blown as a 5-year-old when you discover something like that. That's what we tried to capture.
I feel like all the questions I get from kids, because I work at a zoo, is who would win, a shark or a tiger?
And you're like, are there lasers on the shark? Because
right.
Well, actually, they would never actually encounter one another in the wild. So it's really, there's a problem with the premise of your question.
But isn't there a shark that eats polar bears? I've heard that before.
Oh.
Someone in the chat room was wondering, I think you mentioned this kind of at the beginning, but someone in the chat room was wondering what you think the biggest or most interesting mystery of the universe is.
To me, the biggest mystery of the universe is what happened before the Big Bang. Like, we can dial back the clock towards zero. We don't even really know what t = 0 is, because we're pretty sure that the rules of physics change as you get that hot and that dense. So, we can say like, oh, the universe is expanding and we can run the clock backwards, to crazy density, but we don't even really know what that is. And we have no idea what happened before that. Like, was there some other weird kind of matter which gave birth to our universe? Was there a whole other universe just like ours that crunched and then created another Big Bang? Like, it's bonkers to me that we don't know the answer to this question. Like, in 1,000 years, I hope humans will know the answer to this question, and they'll look back at us and they'll be like, what was it like to live back when they were so ignorant, when they didn't know this very basic thing about their own universe? The way we think about cavemen and cavewomen, like not understanding what stars are, right? The whole context of their life. We're just as ignorant. And so to me, that's one of the most fundamental questions, because it changes your whole relationship with the universe. Like, if you knew exactly how the universe started, that could change how you live your life, right? That has real philosophical meaning. And so that's the kind of question I want the answer to. That's like, if I could speak to the oracle, that's the question I would ask.
So we have a whole bunch of show left. I am enjoying this conversation so much, but I hope that you will want to continue to converse with us about the science.
Yeah, I'm happy to stick around and chat with you guys. It's a lot of fun.
Awesome. In the meantime, where can people find you online if they want to do some Googling and other things?
Well, you can find our podcast basically everywhere podcasts are cast. Daniel and Jorge Explain the Universe. And there's danielandjorge.com. You can find our TV show, pbskids.com/Eleanor for Eleanor Wonders Why. I'm on Twitter at Daniel Whiteson. So, or just Google me. You can find me pretty much. There aren't that many Daniel Whitesons in the world.
People will be able to find you. I think it's great. Okay, everyone. This is This Week in Science that you're listening to. Thank you for listening to TWIS. We are so glad that you are a part of the show and that you are here with us this week. You are the reason that we're able to do what we do every week, bringing you up to date and down to earth views on science, discoveries that happen, and hopefully together we can help bring a sane perspective to a world full of misinformation. It's pretty crazy right now, I gotta say. Head over to twis.org right now. Click on the Patreon link and choose your level of support. That's right. Be a part of bringing sanity and science to more people. If you choose $10 and up, we will be able to thank you by name at the end of the show.
This is TWIS. We're back, and it's time for our COVID update.
That's right. Sad trombone. Okay, COVID update this week. We're just going to dive right into some stories. Hey, do you like mouthwash, Blair?
I was told by my dentist that it's a hoax. So I don't use it. I just brush my teeth and floss every day.
Every single day? Yeah. Well, according to a new study, researchers in Germany looked at 4 different kinds of mouthwashes that are found in pharmacies and also in stores that you can get over the counter. And they determined that while it doesn't completely stop your SARS-CoV-2 infection, it could potentially make it harder for you to transmit because mouthwash kills SARS-CoV-2. So kind of like sanitizing your counters occasionally. Maybe it's if you have an infection or a reason to think that you're infected with COVID and you're going to be going to the dentist, maybe doing a little swish of the mouthwash could help reduce the possibility of you transmitting to other people. Mouthwash. Who knew?
So the part of the problem my dentist has with mouthwash is that it's kind of a broad brush. So yes, you could potentially be killing beneficial bacteria in your mouth. And so I think in this case, yes, if you think you have COVID, mouthwash to your heart's content. But I think that was where, at least some of my kind of concerns about mouthwash as a general daily practice come from, is that you need some bacteria in your mouth.
Absolutely. We need bacteria, bacteria. Yes, we do. But, if there are viral transmission issues, let's see what we can do there.
Mm-hmm. Yeah. Get that virus.
And in the question of whether or not SARS-CoV-2 is aerosolized, whether it's transmitted by just hanging out in the air of a room where somebody breathed, another study has come out, just published in medRxiv this week, which is a preprint server. So take this with a grain of salt because it has not yet been peer reviewed. However, it does fall in line with several other studies that have been done. Researchers looked in a hospital environment in the rooms of patients who had been admitted to the hospital for potential COVID-19 infection. They found viable virus in the air of these hospital rooms up to about 12 to 15 feet from the admitted patients. So this was also without intubation procedures. And the question in hospitals had been to date, when people who work in hospitals are doing intubation procedures, often pulling the tubes out and the airflow issues will result in aerosols with virus in the air. And the question was, is that the only route, or is somebody who's infected just breathing virus into the air? The samples from the patients matched a nasal swab and also these samples that they collected from the room air. It all matched genetically, indicating that, yes, infectious aerosols do get into the air just by infected people breathing. So,
well, I know that a lot
Masks.
of hospitals, when they have the facilities, have been putting COVID patients in isolated airflow rooms specifically. So I know that a lot of healthcare workers have kind of assumed that this is true from the start, but it's nice to see some actual science on that.
yeah, it's the what is the phrase where you try and do the most careful thing to start with, as opposed to waiting for something bad to happen before you start doing something. Yeah,
Abundance of caution. Yeah,
an abundance of caution for sure. So Blair, I want you to talk about the story you brought now, because it follows on this as to, we should be wearing masks when around other people, because if you're breathing stuff into the air. But what did your mask story?
So I saw a study that kind of concerned me because every morning I go for a run and I have a gaiter, one of those kind of buffs around my neck. And that's so that I can run. And then if I see I'm going to pass within 30 feet of a person, I'll pull it up and I'll cover up and then I'll keep running and then I'll pull it back down when I'm far apart from everybody else. Mm-hmm. And so I saw this study with a headline, which always you have to be careful with these headlines, say, wearing a neck gaiter may be worse than no mask at all.
What?
Okay.
As Justin pulls his up over his face. What?
Let me read this. Okay. So there was a recent study that was published evaluating all these different kinds of masks. And the first thing that I will say is that this study was to find a method to evaluate masks. And so they found certain things about the masks they evaluated, but that really wasn't the focus of the study. The focus of the study was the efficacy of the process. What they found was that N95s were the best, of course. So the methodology seems to be good there, because that makes sense. It's because there were no droplets at all that they found on the other side of this mask if someone was talking through the mask. And then when people wore neck gaiters, it was actually the droplet count was higher than if they were wearing no covering at all. So the theory is that it's because it's this thin, stretchy material, it actually is breaking apart droplets into even smaller pieces.
Oh no.
On its way out of your mouth. So
that's not good.
So this is why they say that it could be worse than wearing nothing at all. But they only tested one kind of neck gaiter. They didn't look at all these other variables about them. And, we've talked in the show before about using the candle test, or like seeing if you can feel the wind from your mouth if you try to blow through it. And if it is really thin, as some neck gaiters are, then, these things weren't meant to be masks. They were meant to be like hold your hair back, or soak up sweat around your neck, or any number, or cover your face from dust, things that are not part of preventing the spread of a virus. So it depends on the specific gaiter. Use those tests to see what to use before you go out. And again, this is a preliminary study that actually wasn't even studying the masks themselves. They were studying the efficacy of the test, so that then they could share this test so that people could use it all over the world to test their own masks. And so I really appreciate Kiki actually threw in kind of some of that information here in a rebuttal story for reasons you shouldn't trash your neck gaiter. And so one of them was, yes, the study tested how masks are tested, not which one is best. So that's what I was talking about before. And also this was all tested with one person talking through the same mask over and over and over. So there's all sorts of untested variables there. And this is also just for talking. They didn't test for breathing. They didn't test for heavy breathing. They didn't test for singing. They didn't test for yelling, right? So there's all these general...
So podcasting, yes.
Yeah. There's all these different things that go into what makes an effective face covering. We also don't know if droplet number has anything to do with the risk of transmission, as we were just talking about. So if it's aerosolized, then kind of all bets are off. And then we need to be testing something else entirely instead of the amount of droplets that show up on the other side of the mask. Wear a mask, wear a mask, wear a mask. If you have multiple masks and you can maybe ditch the gaiter, perhaps do that. Or give your gaiter the candle or the blow test to see if it's going to be an effective face shield. But wear a mask.
I think what this underlines for me is just how little we understand about this virus still and how it transmits. And it's like, causing gazillions of dollars of economic damage and killing people. And we still don't really understand this thing. It's incredible.
Speaking about trying to understand the virus, there was a study out this week. I think every week a new study comes out where we find out a little tiny bit more that maybe will get us to the point of being able to control it or treat it. And this week, researchers out of Northwestern University, they were looking at the molecular structure of the spike protein in the virus. The spike protein is what allows the virus SARS-CoV-2 to infect, to bind to cells and infect them. They're using nanometer level simulations, so tiny measures of space, these little tiny things. And when they were looking at it, they found a positively charged site. It's called the polybasic cleavage site. That's located only 10 nanometers away from the binding site on the spike protein that allows for the binding to the cells and the infection. And the positively charged site helps the spike protein bond more strongly. And so now, because they know that it's there, they designed a negatively charged molecule to bind to that positively charged site, and it inhibited the virus from binding to host cells. So potentially, if they can create a negatively charged molecule that can be delivered to patients, people who have been infected, it could potentially limit the infection so that people don't get as infected. They did not expect to find, the researchers say they were not expecting to find electrostatic charges having an impact at this nanometer scale. They were just not expecting to find it. But there we go. Physics in action at the molecular level.
So Daniel, this nanometer scale, is this tiny in your in your line of work, or is that still way macro huge scale?
Yeah, that's like a football field for me. Like I can't even think about stuff that big. It's just, and honestly, one reason I got into particle physics is that it's sort of simpler. Like you just get two little particles banging into each other. You don't have this whole like big swarm of stuff you have to understand, and it's folding and flexing, and it's just so much simpler that way. That's how I see it. But my wife is a microbiologist here at UC Irvine, and she also has been studying COVID, and she's working on she takes samples from the wastewater treatment plant here in Orange County. So basically she's looking for it in sewage, which is quite fascinating. Yeah. So they've seen it, so they can monitor the sort of population level of the virus without like testing anybody individually.
That's interesting.
It's amazing how many new ways we're coming up with for studying this thing. There's so much innovation happening.
I think it's fantastic. The Russians, they say they're innovating and that they have a vaccine that they are moving ahead with, apparently, according to a press release. And Putin, apparently, the report, they've only tested their vaccine on like 76 people so far. Really not that many people. And but Putin says that one of his daughters has already gotten the vaccine, and they are going to move forward with giving it to people, most likely a small cohort of individuals. But based on that, we have no data. We knew that there was a clinical trial happening with this vaccine in Russia, but they have been at the same stage as everyone else doing phase 1 trials. They have published no results, so we have no idea how efficacious or safe this vaccine phase 1 trial was, which is usually not to actually see if it is effective, but just to make sure it doesn't hurt people. Putin says it's fine. And so they're rushing right ahead. The company that is behind the Russian effort is called Gamaleya, and they have developed other vaccines before. And the vaccine that this SARS-CoV-2 vaccine is based off of is one that was being developed for MERS, but they have never actually brought it out of clinical trials. The vaccine is a 2-phase vaccine where they use adenovirus, which is a form of these adenoviruses can cause the common cold. They use, the first shot is adenovirus, I think it's adenovirus 20 or 26, and then the second shot is adenovirus 5. The reason they use different adenoviruses is that if your body decides that it's going to mount an immune response against adenovirus 20, then if you give the second booster shot of the adenovirus 20, then it won't work because your body will have an immune response to it. And so using a different strain, adenovirus 5, for that second booster shot can potentially allow for your body to mount a good response to SARS-CoV-2 and not necessarily against the adenoviruses, which are being used as vectors to infect your cells, to deliver the spike protein, to make your body mount an immune response against SARS. It's complicated. This vaccine is similar to a vaccine being developed by the Chinese, who are still in, I think, phase 2 trials. But to date, similar vaccines have so far been okay. All the results from the phase 1 trials of similar vaccines around the world, they've been okay. They haven't had a lot of negative responses. Kind of like, here, take a Tylenol and call me in the morning. You know, a little bit of fever, a little bit of achiness around the injection point. So it's kind of a standard vaccine methodology. And so it could be fine. The vaccine could be great. And if they're rushing it forward, maybe it'll be all right. But at the same time, they really have not done the safety trials to know whether there will be a portion of the population, which when you get into large numbers of a population size, that could be a significant portion of your population that could have a negative immunological response. They haven't done those tests yet.
Well, and isn't the other side of I guess it's the phase 3 trials that most of these vaccines are in now, isn't that also to see how long the antibodies hang out, like how long you are able to fight off the virus? Because the current thought is it'd be about 6 months, right? So you would need a booster or something like that. But we need to figure that out, because if it's only going to be 6 weeks, then by the time you get everybody vaccinated, then it's spreading again back to the people who you vaccinated 6 weeks ago. So you need to know how long this thing is going to be effective before you do a full-blown launch.
Yeah. Also,
Russian vaccine? Oh, I was going to say Russian vaccine is good 2 years. 2 years.
It just seems like they can't possibly know what the small, sort of the smaller side effects are. You know, like if you do a study with 5,000 people, you don't catch that 1 in 10,000 people's head explodes or whatever. And that's sort of important. You know?
Right. And in order for us to get through this thing, we not only need to know what side effects are and how long it lasts, all this kind of stuff, but we need to project confidence in the process and that we know what the side effects are, because otherwise people won't want it, which is a whole nother problem.
That is a huge...
I know. And mind-bogglingly, we're already in a fragile moment in terms of like confidence in vaccines. I mean, not for the lack of any data supporting them or anything, but like just because of the way they've been projected and the craziness of the internet. So you're totally right. We need to be very careful in safeguarding our credibility as a scientific community. So thank you, Putin.
Yeah. Thanks.
For nothing.
Yeah. Yeah. If you just tuned in, this is This Week in Science. If you want to help TWIS out, why don't you leave us a positive review on your favorite podcast platform today? That would be super helpful. All right, Justin, negative news?
In 2019, Denver voters got to vote on some new public policy which would ban camping in any sort of public area. And so what that, of course, primarily affects is homeless people. So the police started doing a dismantling of homeless camps in all public areas and in areas near waterway, like rivers, because there were people living down by the river, and underpasses and overpasses and down alleys and everywhere. They would clear out any sort of tents and sort of lodgings that homeless people had built and get them out of there. Well, they didn't really, they just got them moving, basically, is what would happen. So there's this study. This was 2 weeks ago. Colorado State Patrol troopers cleared out nearly 200 residents and from one homeless encampment around the Colorado capital. So there was a study that was done by the Bell Policy Center COVID-19 Eviction Defense Project came up with some of this data to sort of look at what happens to homeless people. The study was in collaboration with the advocacy organization Denver Homeless Out Loud, and they had published in the Journal of Social Distress and Homelessness. They looked at police interactions with homeless people in the state of Colorado and the effects that it had on folks since this policy had been created. And mostly it seems to be that people have been forced to go into hiding as homeless people, meaning they're still homeless. You got rid of their tent or their encampment or whatever it is. They're still homeless. They're still out there. They still exist. They have not been put into any sort of affordable housing programs or anything like this. So what those people do in order to get a night's sleep, because they report being bothered by the police so much that they may only get sleep in 2-hour increments before being told to move again. As they go to more and more rural or hidden places, and in those more rural, distant, and hidden places, there's higher incidents of violence that take place when they're outside of the protection that they actually get from being within a city and having police who are preventing abuse of human-to-human contact. What's interesting about this, too, is this is sort of in contrast. This policy was put into place before COVID. And currently there are 420,000 Coloradans at risk for eviction in the coming months.
Wow.
These are many of whom may have voted for this tough love on the approach to homelessness, are now themselves being confronted with the very real possibility of not having a place to live. This is where the Bell Policy Center and the COVID-19 Eviction Defense Project looked at it, and they were seeing that with the eviction moratorium that's been lifted, meaning evictions are allowed to proceed now, the curbed or reduced or ended unemployment benefits. There's about 20% of the United States 110 million renters. If you can imagine, that's about a third of us don't own a home. 110 million, 20% of that. So what is it? It's an easy number. It's 22 million people nationwide are preparing to become homeless by, I think, August. Which, we're there.
It is August.
Yeah, by the end of this month. Yes. Yeah. So anyway,
It's only
that
August?
was, that's,
Yeah.
yeah,
10 years into the beginning of 2020, it's only August.
Yeah.
it's only August. Yeah. So that's like a fun story. Just thought it.
I think I've read social science papers before that have talked about how in the United States, people who are living paycheck to paycheck usually don't identify as poor or low income. There's a disconnect there where people think that they're middle class. Somehow we've all been kind of sold this idea that, like, okay, if you're not like stealing bread for your family, you're middle class. But like, really, there's a huge number of people in this country living paycheck to paycheck. And when this huge disrupt happened and people's paycheck disappeared or changed drastically, suddenly we were put in kind of a bad situation. And you can see how people might not be making decisions as voters for this low income or poor identity that they don't think they have. And now we're kind of seeing the result of that.
Yeah. Good thing there's an election coming.
Yeah, but I'll tell you, I haven't seen an administration that took housing affordability seriously.
So I think American voters are aspirational. A lot of them like to think of themselves as, I'm going to be up there. I'm the next billionaire. I want to allow billionaires to happen so that I could be a billionaire. You know,
Totally. Absolutely.
As opposed to the other perspective, which is if I don't make it to becoming a billionaire, what if everything goes sideways and I can't support myself, instead of thinking of the rescue boat, the way to, I could vote for better policies for housing equality. I can vote for better policies for managing camping. We can vote for better policies. There.
You mean we should have a backup plan that's not being a billionaire? Like, wow, that sounds wise.
Baby!
It's billionaire or bust for me, man.
What's your backup plan?
In the lottery.
Actually, my plan is I'm going to be a multi-billionaire. So my backup plan is to be a billionaire.
Well, the wealth income disparity in this country reminds me very much of that infographic I saw on the differences in black hole sizes. The spectrum of the black hole sizes, where there's somewhere that are like all of the other black holes all put together don't amount to but a speck in that black hole. Is the difference between somebody who's a billionaire and a working class person who,
Are you saying Jeff Bezos is a supermassive black hole on our economy?
He is sucking in all the money. So I would say so.
Well, that's the problem, right? At a certain limit, we're going totally off. At a certain limit, that money just goes into a black hole. It doesn't come back into the economy. So it's just
Let's move away from the economy. And this conversation is so important to so many of us and the current events of everything right now. But it's stuff that we need to think about. All right, moving on to more science. I have some shrinking dwarfs. We were talking about the universe and the Milky Way-like thing 12 billion years ago. Well, curious thing about white dwarfs. White dwarfs are stars that as they gain mass, eventually at some point they implode and they turn into supernovas, type 1a supernovas. So white dwarfs are these really cool stars, and an interesting hypothesis that astronomers had for a very long time. There was this size trend that they observed a long time ago in white dwarfs, and they thought, they're like, okay, well, maybe this backwards relationship happens that the more mass a white dwarf has, the smaller it actually gets. But they haven't had any data to support it until now. Researchers used the Apache Point Observatory in New Mexico and the European Space Agency's Gaia Space Observatory to look at a bunch of white dwarfs and to look at the luminance of these white dwarfs, basically measuring how bright they were. And so then they're like, okay, this is how bright you are. So this is pretty much how big you are. But then mass, they wanted to know exactly how massive they were. And you can't get that from the light. So they looked also at gravitational redshift, how much light is shifted as it moves past the dwarf. And as it gets stretched out into redder wavelengths, they could determine whether the dwarf was more massive or not. Okay, and so what they did indeed find is that as they looked at a bunch of white dwarfs, the measurements really matched the theoretical predictions. White dwarfs with about half of our sun's mass were about 1.75 times bigger than the Earth. And then those with more mass than the sun were about 0.75 times the width of the Earth. So as they became more massive, gained more mass, they got smaller and smaller and smaller. So what explains this? It's something
sort of gassy threshold going on.
Yeah, what they call it, that the material electron gas becomes exotic, and that the electrons in the white dwarf are what they call a degenerate electron gas. And this is not a put down, it's actually a term. The degenerate electron gas, the electrons in this gas has to squeeze together. So it's the electrons pack closer and closer and closer together so that they have enough pressure to hold the star up. so that the star doesn't just collapse under all that mass. So it's this very interesting relationship that occurs, that the more massive the star becomes, the more packing occurs. And so it gets tighter and tighter and tighter and smaller and smaller and smaller until eventually there is a limit reached. And yes, the mass of the star collapses and then you have a supernova. But until that point comes, as white dwarfs gain weight, gain mass, they actually thin down.
That's not happening to me during the pandemic.
No, me neither.
White dwarfs are amazing. And I think there's something people don't often realize about them is that they are stars technically, but they're not glowing from fusion. It's not like there's, fusion happening like in the center of our stars. They're just like big, hot, leftover blobs of stuff that are gradually cooling. And eventually they'll just cool so far down that they'll become what they call black dwarfs. But it takes longer than the current age of the universe. So we don't think there are any black dwarfs currently in the universe, but like there will be an age of the black dwarf when eventually these white dwarfs become black dwarfs.
And that'll be probably, it'll be at some point when the universe has expanded so far that we wouldn't be able to see them anyway.
Yeah. Yeah. And, they won't be radiating as much because they'll be cooler.
Wait, yeah, if there was one out there today, could we see it?
Yeah, great question. Probably not. I mean, if it's out there and it's not actually a black hole, it would still be radiating, but just in like really long wavelengths. So I suppose you could see it in the radio, but it'd probably be pretty faint. So it's probably what you can do is set some limits on, how many there could be. Otherwise, we would have seen them. But also theoretically, we just don't expect them to exist yet because we're still in the early days of the universe.
Wait a minute. We're in the early days of the universe?
Yeah, well, we don't know, right? Will the universe go on for another 10 billion years, another 10 trillion years, quadrillion years? I mean, we look back at like the beginning of the universe, we're like, oh, the first few 100,000 years, like, things were just getting warmed up. This could still be warm up, right? Aliens or humans in a quadrillion years could look back and be like, oh, back then when the universe was still expanding and stuff was hot and dense, we just don't know what the scales are.
I have a brain story and then
Shocking.
Shocking. Researchers at Michigan State University found that even when people know that they are taking a placebo, the treatment is linked to a reduction in brain activity that's indicative of emotional stress. They got people to come into their study, and this is published in Nature Communications. They say the placebos are all about mind over matter. Non-deceptive placebos were born so that you could possibly use them in routine practice, so that rather than prescribing a host of medications to help a patient, you can give them a placebo, tell them it can help them, and chances are, if they believe it will, then it will. The researchers wanted to test these non-deceptive placebos to find out if they actually helped people. In the experiment, they told people that this nasal spray, which was saline, was a placebo, that it had absolutely no active ingredients, but would help reduce their negative feelings if they believed it would. And then they had a control group that inhaled the same saline spray, but they were told that the spray would improve the clarity of the physiological readings that the researchers were recording. And then they recorded brain activity and found that the placebo, the non-deceptive one, where people were like, okay, it's a placebo, fine, it's not going to do anything. It did basically the same thing that the placebo for the people who were told it would be doing something did. It reduced emotional distress activity, electrical activity in the brain. So, I mean, there are a couple of questions here related to, the correlation of, hey, you're looking at electrical activity in the brain. Is this really indicative of that emotional duress? And is that really what you're measuring? However, the idea that you would have the same exact or very similar responses when you're told that something's not going to work. as when you're told that it will. That
you're being lied to.
I have two takes. I have two quick takes on it. One is that if I was being told you're getting the placebo, this does not have the active ingredients, I'm like, yeah, right.
You'd assume you're getting.
Yeah, this is like a double, triple blind kind of thing where you tell everybody it's a placebo, but you're the only ones that know later. You find out and then you see the difference. And the other thing is we know that there are like super responders to placebo. So there are some individuals who heal from a placebo or go or find a really transformative thing, whether it's their energy or the whatever was affecting, that absolutely respond as though the treatment has worked. So there is this they might not have caught it in this study, but there's this weird segment that they have to try to figure out how to identify, because they can ruin a drug trial.
What I'm wondering is, this is a nasal spray, right?
Yes.
So are we sure just having more moist nasal passages
makes you feel better?
Yeah.
That's the discovery they're not talking about.
Connected, right? It's all connected.
Saline nasal sprays
when your sinuses are messed up, it kind of messes with your brain and everything. You're all disoriented. Maybe actually this isn't a placebo. Maybe wetting your nasal passages is like good for you.
Hey, Dr. Justin's not a real doctor. Nasal treatment reduces stress based on placebo technology derived from science. Let's package that. We'll put that up there with our face masks and the mugs.
I don't know. Yeah. I'm just throwing it out there because your nasal turbinates are supposed to stay moist. So
it's a great point, and it gets at, is there a mechanism? There's something happening. What is the mechanism? Is it from the brain going, I feel happy? Or is it, is it that, there's moisture in the sinuses for this particular study, and that leads to a response in the brain? And then, what is the pathway?
Volunteering to help science, taking some time out of it. Maybe that's the thing that's giving you a better
science. Feel good.
Yeah, I'm contributing to science right now. I'm part of this very important study. Oh yeah, I can already feel it. I can already feel that working.
From a research standpoint, though, being able to use something like a non-deceptive placebo to have the same effect as a placebo, but not the ethical conundrum that maybe a researcher would be under, that knowing that a non-deceptive placebo can have the same or a similar effect may allow studies to take place that couldn't happen otherwise because of potential ethical issues. To
me, it rings a little bit just of like suspension of disbelief. Like, you go in to see a movie, it's fiction, it's made up, it's actors. You can still get into it. You still have reactions. You jump out of your seat when the zombie comes out of the closet. Like, there's a part of your body that has bought in, even though you know as a fact that it's not true, but you still participate emotionally. So maybe there's part of that happening.
And it could be the participation that is the key, that maybe it's the act of taking a pill, the act of using the nasal spray, that participation, like you said, maybe that allows some amount of buy-in, whether or not it's deceptive. Yeah. Anyway, placebos, they're crazy. We really don't understand them. It's pretty awesome. A very interesting effect that definitely needs to be taken into account. This is This Week in Science, and we have made it to that point in the show that so many people wait for.
I know I do.
I know you do. It's time for Blair's Animal Corner.
With Blair.
Your girl, except for giant pandas and squirrels. There's Animal
What you got, Blair?
I have a story about Tuataras. Do you know what a Tuatara is, Justin?
I got one of those when I was like 9 years old. It had the joystick with the one big red button, and like came with the games weren't great, but it was like still the best thing you could get.
That's an Atari. Huh? No, this is a Tuatara.
Oh.
It's a reptile. It looks like a lizard. If anyone who was not a biologist or a zoologist saw this animal, they'd go, "That's a lizard." It's not a lizard. It's not a lizard. It's a rare reptile from New Zealand, and it is the only remaining member of Sphenodontia. So when we think about reptiles, we have lizards, we have snakes, we have turtles, we have crocodilians, and we have tuataras. They are their own thing. And there's lots of debate about what they are more closely related to. Are they more closely related to birds and crocodiles, archosaurs? Are they more closely related to turtles? This like kind of question mark dotted line where we don't know exactly where they belong on the family tree. Or do they belong to a shared ancestor with lizards and snakes, since they look so much like lizards? And so this is the first sequence of the Tuatara genome. And they have been able to kind of draw some conclusions from there. So this was a global team of researchers. They partnered up with Maori tribes to sequence the Tuatara. And they found that they are, in fact, more closely related to lizards and snakes, and that they diverged about 250 million years ago. And that is a long
this is
period.
A tiny dinosaur. This is a tiny living dinosaur.
Yeah,
oh my goodness.
So these guys have been separate from lizards and snakes for so long that this might be why this genome, as far as they can tell, is super unusual. It has a lot of repetitive DNA segments that are unique to these guys and that have no known function yet.
Yet, that's the key.
Yet. They are predominantly nocturnal animals, but their DNA carries a high number of genes that are involved in color vision, which means they're doing something during the day. So their current theory is that it helps juveniles escape from predators. Here's the other crazy thing. Lizards live, I don't know, maybe if you're lucky, 20, maybe 30 years. Tuataras can live to be over 100 years old.
Wow.
So
let's study that.
Yeah. So scientists examined some of the genes that appear to be used to protect the body from aging. They found that the Tuatara have more of these genes than any other vertebrate species they have yet sequenced. So they got something going on in their genes that helps them live so long. They also don't appear to get many diseases. So looking into the genetic factors there could be pretty helpful.
Where do they live?
New Zealand. And that's where we run into trouble. They aren't doing great. And it's because of rats. It's because of invasive rats. So this is an animal that is being protected. That's why the researchers worked with Maori tribes to study these guys safely and to study their behavior as well safely. And so the more we can know about their genome and their biology, the better we can conserve them, since we can understand what they need from us to succeed. They used to thrive in New Zealand, but then about 800 years ago, the first settlers brought rats. And the real problem with the rats is that the rats will eat tuataras more quickly than they can reproduce, because remember, they live 100 years. Sometimes it takes them over 10 years to reach sexual maturity. And then they only produce young every 2 to 5 years after that. So this is the whole problem with sharks too. Sharks need to get super old before they can have babies, which is part of the problem why shark hunting can be such a big problem. They can also be pregnant, some sharks, for multiple years before they give birth. So it's a similar life strategy here that they are. Yeah. What?
I got the solution.
Yeah,
we can get rid of all these rats on the island by importing cats.
Oh, great! Except remember,
cats kill all.
cats are already killing numbats and other native marsupials to New Zealand.
Oh, no.
Yeah.
Yeah.
Well, how do these animals keep getting there?
Humans.
Ah, I got Blair.
Yeah.
No, I'll get in trouble for that one.
No,
we can't do that.
no.
That won't work. No.
Too late, I think, for that one. But yeah, so we have sequenced the Tuatara genome. We now think they diverged from lizards and snakes about 250 million years ago and have a lot of kind of a wealth of information located in this genome that is just waiting for us to study. So there's that pile of data that has all sorts of cool stuff that hopefully we can all benefit from in the future. Maybe there's some great genetic code that can prevent us from getting diseases. Maybe there's something else that can help me live to be 250 years old.
But the part about that, though, I'm a little suspicious about the diseases thing.
Yeah.
Is how many diseases is this lizard encountering?
Yeah, in New Zealand.
Or are they like throwing stuff at these lizards and like they don't get this, they don't get that, or just they don't seem to be getting sick where they're at?
I think it's more that one. Yeah. So we don't. I mean, they only live on New Zealand. So
yeah, put one of those Tuataras in New York City, living on the streets for a couple of months, and then look and see what diseases they actually can and can't get. That's
what happens when they meet the New York City pizza rat, right?
Yeah.
I think the New York City pizza rat would win even faster.
The New York pizza rat would beat the New Zealand jungle rat.
Maybe getting so used to melted cheese, they wouldn't want to eat the Tuatara. I don't know. Melted cheese.
It's not real mozzarella. It's not. They don't have that.
No. So that's my story about the Tuatara. But also, I should have done this one first. I have to end the show on kind of a sad note. Climate change. I have to talk about climate change. Or more specifically, the redheaded stepchild of climate change, ocean acidification. So we talk about all the CO2 in the atmosphere. We talk about climate change. We talk about the warming planet. We talk about the sea ice. But also we need to talk about what happens to about a third of that carbon dioxide, which is it gets reabsorbed by the ocean and it changes the ocean's chemistry. So it affects the overall pH of ocean water because there's all these little free hydrogens floating around. So anyway, this is a study from University of Connecticut looking at fish's impacts on fish from ocean acidification. So when we think about ocean acidification, usually scientists aren't that concerned about fish because things like bivalves or sea urchins, they are extremely sensitive to changes in pH. But fish, as far as fish researchers know, ichthyologists know, is they are active, robust animals. They have a fantastic acid base regulatory capacity. And so they're not that worried about fish. Thankfully, there are still researchers checking that hypothesis. And so this was a study looking at a small, shorter-lived fish called the Atlantic silverside. This is so they could study the fish across its life cycle, across several independent experiments over the course of 3 years, rearing them under controlled conditions from the moment the eggs are fertilized until they are about 4 months old to see if there were effects from elevated CO2 conditions. They tested CO2 levels at two different levels, present day levels and the maximum level of CO2 in 300 years under a worst case emission scenario. So basically they had to take this fish that already was kind of tolerant to pH shift because otherwise they'd just kill a bunch of fish in the lab. They wanted some fish that they knew were hardy enough to handle this experiment. And so they went for this worst case scenario so they could kind of overcompensate for that and see, okay, really, if the CO2 levels just totally spike, what's going to happen? And actually, these fish, the ones that were exposed to higher levels of CO2, didn't grow as large. So we could see potentially the extrapolation here is you could see global fish populations shrinking over the course of this kind of longer longitudinal change in CO2 in the oceans. So the reason this kind of caught my eye is that there have been lots of studies about mammals living at high altitudes shrinking from climate change. And now let me clarify. Individuals are not shrinking. The average size that animal grows to is decreasing. So in the case of animals living on mountaintops, it's because they actually are getting pushed to higher elevations because it's too hot where they're used to being. So they go higher up in elevation. There's less oxygen in the air. And so they have to kind of work harder to survive and grow, and they don't grow as large. So within this case, the CO2 appears to just be a stressor that is reducing their ability to grow up as large. They also checked for sex differentiation because we've seen with other things that different chemical cues,
turtles, right?
Can impact that. And so there was no impact on the proportion of males and females by high CO2. So that is good. But again, if you rear these fish under ideal conditions and feed them controlled amounts of food, you don't overfeed them, then high CO2 conditions reduce their growth in measurable amounts. This is a deficit of about 5 to 10%, which in these teeny tiny fish is only a few millimeters overall, but the results are consistent, and that does impact biomass in the ocean, which does have overall impacts on ecosystems, food webs, all sorts of things. Not to mention that if this is something that extrapolates to larger fish, that it could end up being a much bigger difference. So
what I find curious about this, and I would love to contrast this, we had a wonderful conversation with somebody who was studying shark scale, which are basically like tiny shark teeth, and looking at different ocean fish sizes going back in time. I would love to correlate this with that because Megalodon was the largest shark that ever swam the oceans. Was there at like a 400, per parts per, that we're approaching now and the atmosphere. So if the largest shark that ever existed in a time when there was a high carbon atmosphere, then something must have been eating something well enough to
as it usually comes down to with climate change, it's all about time scales. So that parts per million happened over a much longer period of geologic time. And so the animals that lived in the ocean had a higher tolerance for that higher parts per million. We're talking about in just basically a snap of the fingers, the pH completely changing in the ocean in a way that animals are not used to, and that being a stressor. What's interesting is this study looked back at previous studies looking at fish size in relation to carbon dioxide levels, where these previous studies didn't actually find a difference at all. And what they found was these studies were not regulating the amount of food that they were giving the fish. They were letting the fish eat their fill. And so it looks like the CO2 is a stressor. They were able to compensate for that stressor with additional food. But if you maintain the same amount of food that the non-stressed fish get with the stressed fish, then they do not grow as large. So it's all about these large scale changes that are happening quickly. Can animals adapt quickly enough to get used to this new normal? Can plants move fast enough to get back to where they're supposed to be? All this kind of stuff. So this is exactly what this is about, is in this kind of snap of the fingers, climate change, changing the temperatures on our planet, ocean acidification, changing the chemistry in the ocean in a way that is too quick for plants and animals to adapt to. I know.
Just like the white dwarves, they're shrinking.
They're shrinking. Yes. Poor little fish. All right, so let's end this show on a fun, good note. I have a letter for our This Week in Science questions. This week, there is a "What has science done for me lately?" comment included in this letter from Eric Combs. What has science done for me lately? Well, I went on a trip to Munising, Upper Peninsula, Michigan. I don't know if I pronounced that correctly. Thanks to the hard research work of geologists, I was able to learn about geological strata, back in college. Thanks to chemists and other scientists, we were able to learn about the elements, especially those we see in geology: iron, manganese, calcium, copper. What am I driving at? Well, for me, science can enrich and enhance the beauty of nature. Science does more than propel us forward technologically. It can also help us find new ways to activate our PNS to reduce stress and bring enjoyment to our existence. Everything from tiny arthropods to giant celestial bodies beyond our atmosphere. Yoga and body mechanics, progressive relaxation and mindfulness. Science helps me appreciate the beauty everywhere around me, even in these tumultuous times of civil unrest and COVID-19. Knowledge is never a prerequisite for appreciating beauty, but it can help enrich the wonderment of everything around us. Science needs us to continue to explore the world each day with awakened curiosity. Science question. If science wasn't cool, then why is it possible to spell nerdy with the periodic table of elements? Nitrogen, erbium, dysprosium. Anyone want to take a gander at answering that question?
I think you just proved it.
Clarify, it's just nerd, not nerdy. Is that right?
It's nerdy because it's DYSP.
Oh, is it? Okay. Oh, it's nerdy. Okay.
It's nerdy. That's right.
Well, to borrow Blair's answer, I have a problem with the premise of the question, right? Because science totally is cool.
It is. Exactly. Always.
Yeah,
it's like its own Mobius strip.
We can always, the universe itself is cool.
Nerdy.
At the Kelvin
cooling.
Scale. Cooling.
At every scale, life is just improbable, impractical, and possibly everywhere, but also could not be anywhere else but here. How can we be on this planet for this limited period of time and not be curious about observing the universe? How can we be on this planet for this limited amount of time as a sentient species and not want to learn everything that we can about it? How can we fixate so much on things that are just transient details that we made up to help mechanically make it through a day when all of this wonderful stuff is out there and this is the one chance we'll have to glimpse it? I don't know. I think we should probably I'm doing a science podcast, so I'm maybe biased on what I find interesting to think about while being alive on the planet.
Maybe that's the answer to the Fermi paradox. Maybe life is everywhere, but we're the only curious ones, and everybody else is like, who cares what's out there?
Yeah, whatever.
Hope not.
I think we have made it to the end of the show. On that note, thank you for listening. I hope you enjoyed the show. Thank you, Daniel, for joining us tonight. It has been wonderful to have you on the show to tell us about your work, to talk with us, explain the universe. Where can people find out about you? You want to send them one place?
Yeah, just go to danielandjorge.com. You'll find our podcast there.
All right, it's time for shout outs. Shout outs to Fada for his help with social media and for show notes in the YouTubes. It's always well done. Gord for manning the chat room. Identity4 for recording the show. And I would like to thank all of our Patreon sponsors and the Burroughs Welcome Fund for their generous support. Donathan Stiles, a.k.a. Don Stylo, John Scioli, Eric Combs, Flying Out, Guillaume, John Lee, Ben Rothig, Ellie Coffin, Maddie Perrin, Gaurav Sharma, Josiah Zahner, Mark Shoemaker, Sarah Forfar, Donald Mundis, Rodney Lewis, Stephen Albaran, John Ratnaswamy, Dave Friedel, Daryl Myshak, Stu Pollock, Andrew Swanson, Fred S104, Corinne Benton, Sky Luke, Paul Ronovich, Ben Bignell, Kevin Reardon, Noodles, Jack, Sarah Chavis, Paul, Jason Olds, Brian Carrington, Matt Bass, Joshua Fury, Sean and Nina Lamb, Sue Doster, John McKee, Greg Riley, Mark Hessenflode, Gene Tellier, Steve Leisman, Ken Hayes, Howard Tan, Christopher Rappin, Richard, Brendan Minish, Melazond, Johnny Gridley, Richard Porter, Christopher Dreyer, Mark Mazzaros, Artyom, Greg Briggs, John Atwood, Robert, Rudy Garcia, Dave Wilkinson, Matt Sutter, Philip Shane, Kurt Larson, Craig Landon, Mountain Sloth, Jim Drapeau, Alex Wilson, Dave Neighbor, Kosti Ranke, Matthew Litwin, Eric Knapp, E.O., Kevin Parachan, Aaron Luthen, Steve DeBell, Bob Calder, Marjorie, Paul Disney, Patrick Pecoraro, Gary S., Ed Dyer, Tony Steele, Ulysses Adkins, Brian Condren, Jason Roberts. Thank you for all of your support on Patreon. And if you are interested in supporting us, you can find information at patreon.com/thisweekinscience, or just click the Patreon link at twist.org. Next week's show.
We will be back on Wednesday at 8 p.m. Pacific time. We will be broadcasting regardless next week from our YouTube and Facebook channels and from twist.org/live.
Hey, do you want to listen to us as a podcast if you're not already right now? Just search for This Week in Science wherever podcasts are found. If you enjoyed the show, get your friends to subscribe as well.
For more information on anything you've heard here today, show notes and links to stories will be available on our website, www.twist.org. And you can also sign up for our newsletter.
Hey, you can also contact us directly. Email Kirsten at kirsten@thisweekinscience.com, Justin at twistminion@gmail.com, or Blair, me, at blairbaz@twist.org. Just put twist, TWIS, in the subject line, or your email will definitely end up inside a supermassive black hole.
You can also hit us up on the Twitter, where we're at Twist Science, at Dr. Kiki, at Jacksonfly, and at Blair's Menagerie. We love your feedback. If there's a topic you'd like us to cover or address, a suggestion for an interview, a haiku that comes to you tonight, please let us know.
We'll be back here next week, and we hope you'll join us again for more great science news.
And if you've learned anything from the show, remember,
it's all in your head.
This Week in Science. This Week in Science. This Week in Science. This Week in Science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand. 'Cause this week's science is coming your way. So everybody listen to what I say. I use the scientific method for all that it's worth, and I'll broadcast my opinion all over the earth. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. This Week in Science. 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 I've got one disclaimer, and it shouldn't be news, that what I say may not represent your views, but I've done the calculations and I've got a plan. If you listen to the science, you may just yet understand that we're not trying to threaten your philosophy. We're just trying to save the world from jeopardy. Jeopardy. And This Week in Science is coming your way. So everybody listen to everything we say, and if you use our method instead of rolling a die, we may rid the world of toxoplasma gondii. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. This Week in Science. 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 Got a laundry list of items I want to address, from stopping global hunger to dredging Loch Ness. I'm trying to promote more rational thought, and I'll try to answer any question you've got. But how can I ever see the changes I seek when I can only set up shop 1 hour a week? This Week in Science is coming your way. You better just listen to what we say, and if you've learned anything from the words that we said, then please just remember it's all in your head. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. This Week in Science. 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 This Week in 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 Science.